So today we are learning about the linear algebra. That is the 5th semester. It is a core. Okay. So I think so 2 or 3 classes offline you have conducted. No, in all centers they have conducted the classes. So regarding of the linear algebra in 4th semester, you have studied about the groups, no, groups and rings. So if you know the concept of groups and rings, here we can easily, that is in linear algebra, we have the concept of the vector space is there. So if you have the textbook, so try to open that one. And one more thing, I hope so, you know that the examination pattern has been changed, you know. So that is objective type questions are not there. So you are able to listen my voice, no?
Yes, ma'am.
Okay. First and that is section 1 and section 2 is same. Third section, whatever the objective questions are there, so that they have taken out, and only long question is there. That is which carries only 20 marks. Okay, so only 2 questions will be there. That is the 2 questions you have to write any one question which carries 20 marks. Okay, from these all whatever the 4 blocks are there, from the 4 blocks they may give the combination of any 2 blocks, or from one block only they will give one question, means almost which suits for the 20 marks. So whatever the theorems are there, you might be knowing that linear algebra, the 5th semester, it is similar to the 4th semester. So 4th semester all theory is there, no? You have the concept of groups is there, and also rings is there. So how you are having the theorems, almost the linear algebra also will be like that only. And here also just definitions are there. In that algebra 4th semester, you have the definition of group is there, subgroup is there, normal subgroup is there, cosets are there. Okay, and also homomorphism of groups is there. So it is somewhat almost similar to the algebra. So how you are having the definition of a group, so you might remember that for the group, so you will denote it as for the capital G, and we will use the one binary operation, that is plus we will use, or else we will use that is with the help of G comma plus. So for the group you will have one binary operation, and for the ring we will use the 2 binary operations. For the ring we use the 2 binary operations, that is plus and also dot, which we call it as a multiplication. Okay, so G comma plus, if you to show that G comma plus is a group, it has to satisfy the 4 properties. Okay, you might be knowing those properties also. First one is the closure property you will have, and the second one is associative, and third one is additive identity, and fourth one is additive inverse. Okay, then we call G comma plus as group, and we call that group as a abelian group, means if it satisfies the 5th property, which we call it as a commutative property. Okay, so closure means any 2, so A comma B, if they belongs to G, then implies A plus B belongs to G, that's set G. So that is whatever the binary operation is there, when you do the addition of any 2 numbers, whatever the resultant you are getting, if that belongs to set G, then we call it as it is satisfying the closure property. And associative means A plus B plus C is equals to A plus B plus C. So additive identity means here additive identity element is a 0 we have. So here we'll take it as A plus 0 is equals to 0 plus A is equals to 0. So additive identity element is 0 here. Inverse means we'll write it as A plus minus A or minus A plus A is equals to 0. Okay. So this is the property of additive inverse. And commutative means we'll have A plus B is equals to B plus A. Okay. So if, in the ring, we'll write it as R plus comma dot, that is ring R. So that means with respect of plus, it satisfies all these properties, and with respect of multiplication also, it satisfies all those properties. Then we call it as a ring. Okay. So same abelian ring. Abelian ring means if it satisfies commutative property, then we call it as a abelian ring. In that also you have the subgroup will be there, and also subring will be there. Ideals are there, cosets are there. Just before starting this one, if you have go through the 4th semester algebra, then you can understand the concept of here this one. So even in rings, you have studied the field concept is there. So field concept means if any we are taking the set, a field will denote it as a capital F. If field it satisfies the properties F comma plus is an abelian group, and also F comma dot is an, that is with respect to of addition and with respect to of multiplication if it is abelian group, and also with respect to of dot also if it is abelian, then we call it as a field, and also it satisfies the distributive laws. So if F satisfies with respect to of plus abelian group, and also with respect to dot also, if it is satisfying the property of abelian, then we call, and also third one is the distributive property, you know, no, A dot B plus A dot C. Okay. So this distributive property also, if it satisfies, then we call it as a field. So here in linear algebra, so you know each and every whatever the concepts are there, real analysis means it deals with the rational numbers and all, that is a real numbers. So how we have for the different topics, that is the first one, you have the differential equations is there. Next, first semester you have differential calculus is there. Second semester differential equation. Third one is the real analysis. Fourth one is the algebra you have. And fifth one is the linear algebra. So here, whatever the linear algebra is there, in that we'll study about vector spaces. And also system of linear equations is there. If you see the textbook, blocks are there, no? Each block 1, block 2, block 3, and block 4. Okay. So here linear algebra is a branch of mathematics. So it is also one of the branch of mathematics. It is dealing with the vector spaces and also linear equations. So linear algebra, it is the main topic of that one. In that whatever we are dealing, we are dealing with vector spaces and also linear equations. Almost these linear equations will come under the matrices. So if you have the idea about the matrices, those equations will be in the form of linear equations. So with the help of that, these two topics are there. First, whatever first block is there, and second block, it almost these two blocks covers the vector spaces. And third one is about the linear equations is there. And fourth block is about the, that is inner product space is there. So in that is almost similarly like this only will be there, but it's somewhat difference will be there. Okay. So I hope you even know the concept of vectors. So actually in physics, the whatever the vectors are there, they are considered as the for physical quantity. That is, if they have both the direction and magnitude, then we call them as a vectors. If only magnitude is there, then we call it as a scalar. These are definitions for the physical quantities. That is, in physics, we'll use them as the vectors. Whereas when we are going in the mathematics, we'll consider these vectors as the number, that is, we'll denote it with the V. Okay. So here also same concept will be there. vectors will be there and also scalars will be there. Here, whatever the scalars are there, almost we consider them as the real numbers. So scalars are the real numbers and vectors are, we usually we denote them with UV. That is a small u and small v, and vectors denote with capital V. Okay. And scalars will take from the set that is filled. So if you know the definition, whatever given in the textbook, we'll write the vector space as V of F. And here, I have told that in physics, we'll use the vectors for finding the magnitude and also direction. So in mathematics, in 2D and 3D. So 2D means you will have the 2i means will you take the vectors, no, I, j, k vectors, and we'll represent the vector like this, no, on the, if A is any vector, okay, in 2D means only 2i plus 3j. So this is the unit vector along x-axis, and also this is the unit vector along y-axis. This is the vector A. We are writing in the, this is along x-axis, and this is unit vector, okay, unit vector, and this is the same along y-axis. Okay, if we have one more, so this is along z-axis. So only 2 means we'll do in the 2D, and if we have the 3, then we'll okay. Okay, this is in 2D we'll take only 2 vectors, that is 2i plus 3j. In 3D means we'll deal with the 4 vectors which are along x-axis, y-axis and z-axis. We know even in like this, no, if this is in the 2D we'll take, and if in the 3D we'll take this one, okay. So here those vectors we are doing in 2D and also 3D, then we call them as the only vectors. So when we go to the vector space, okay, in the name itself it is having the space. Space in the sense it is not 2D or it is not 3D, not even 4D. So up to nth we'll find, no, nth terms we'll find even in the for the square root and also cube root. So in such the vectors which we are finding for the nth terms, we call it as a vector space. Okay. So for the nth, it may be 2D you can find, 3D you can find, and 4D also. 4D is somewhat typically it will be there, after that 5D, 6D, like that only. And for the nth dimension, so for the nth dimension, we'll use the concept of vector space. Okay. So here we have the first whatever block is there, it deals with the definition of what is vector space. And in that you have many theorems are there. So the theorems also important. And sometimes they will even ask the definitions, what is a vector space? And what is, even in this also you have the subspace is there. So group is there, no? Group, subgroup means any another will take, if S is any set which is subset of G. Okay. S is any set which is subset of G, which is satisfying all these 4 properties. Then we call this set S as a subgroup. Okay. Ring also like that only. If you take here S dash is there, any set which is subset. I hope you know the concept of subset. Subset means almost it is having the elements which are the half of the elements will be of the set R. Okay. Subset means whatever the first set will be there, from that some elements you have in that set and which satisfies the properties of this one. If this S dash is a set, if it is satisfying all the properties of R to become a ring, then we call this S dash as set as a subring. Here also same. S is any set which is satisfying all the properties of this G, then we call this S as a subgroup. Even in vector space also, subspace means we'll denote it as capital W it is. Then if it is satisfying all the properties of vector space, then we call it as a subspace. Okay. So many definitions are there. I have told already that it is a theoretical one. So many concepts are there in this all two blocks. So first one is definition of what is a vector space. After that, subspace is there. Then after that, linear span is there. After that, linearly independent vectors, linearly dependent vectors, and linear combination is there. If you know these are all concepts, then only we can do the theorems. Okay. So first, so if you have the textbook, please open that and see the contents is there, no, in that block 1 and block 2, block 3, block 4 are there, no. So just today we'll go through these, whatever the units are there and what are the important topics and whatever you have to study for the examination point of view. I will tell those, and from the next class we'll go through some theorems, and also third block and fourth block. If you are perfect in these two, these are somewhat problematic one. Means the third block is a matrix, characteristic values and vectors. So intermediate, if you have studied, you have the concept of that is Cayley-Hamilton theorem is there, no, rank of the matrix, non-singular matrix and singular matrix, rank of the matrix, and the cofactors will be there, no, minors, how to find the determinant of the matrix. That concept, if you know, you can easily score that is one long answer you will get, two short answers you will get from block 3. Normal form also will be there to find the rank of the matrix. That is, if you convert the matrix into any identity matrix, 2 by 2 identity matrix or 3 by 3 identity matrix, then we call it as a normal form. And finding the rank of the matrix and solution for the linear equations will be also there. So only third block you are having the problems are there. That is also regarding of the matrices. And whatever the fourth block is there, fourth block is also almost theorems are there. Means that only some named theorems are there. You will go to the triangle inequality is there, parallelogram law is there, and Gram-Schmidt orthogonalization theorem is there, and also Squar's inequality, Bessel's inequality. Somewhat only these theorems are there which are important for the examination point of view.
రెండు వాటర్ ఒక పాల
Okay, so in this you will have the
Please, can you please explain the exam pattern?
Yeah, I am telling the important questions which you will get from the block 1, block 2, block 3 and block 4. Okay. So those theorems and also the problems, if you study, it's enough for you as the examination point of view. Okay, first one, if you see block 1, it is the vector spaces and basis is there. So in this basis and dimensions, even you have in the practical classes also, what regarding of the vector space definition, you have the solving the problems. Okay, any R here represents the field of real numbers, so we consider the real numbers. So in that you will have the standard basis will be there. So standard vectors means if it is a R2 means 1, 0, 0, 1. So that if it is having the standard basis of R2, R3, R4, you have to show that it is a vector space. So first thing in page number 2, if you see, it is a definition of the vector space. So first one is you have to show that V of F, we call it as a vector space. That is vector space over the field F. Vector space over the field F. You see in the textbook, in theorems also, anywhere you will find the term which it is called as a V of F. Okay, it is called as a vector space over the field F. Okay, here this V is the vectors and this F is scalars. Okay, this is the field of vectors, this is the field of scalars. So here vectors means usually we'll take them as U comma V. And for scalars, we'll take it as A, B, C, like these elements. Okay. So in this definition, which it is called as a V of F, means vector space over the field F, it has to satisfy some properties. So 10 properties will be there. If it satisfies those 10 properties, then we call it as a vector space. So that definition is important here. Whatever vector space definition you have in the textbook. So it is let F be a field. Here F is a field. So and we'll take F elements as scalars. Scalars means all real numbers. Okay. Here whatever the vectors we are taking, those vectors we'll take it as U comma V. And these are scalars. Okay. So with these two combination, you have to find some properties. If any set is satisfying these all properties, 10 properties will be there, then we call it as a vector space. Okay. So definition is the important one. You may get for the 5 marks. Definition and any, you will ask the examples. So which numbers are real numbers or rational numbers, and also, so real numbers means it is a combination of rational and irrational numbers. So set of real numbers will satisfy all those 10 properties. So example for the vector spaces, one is the real numbers and also another one is the rational numbers also. Q also satisfies all the properties. So it also becomes the vector space. So here if you see the definition of this one, all the properties are here. So first F is a field, a non-empty set V is said to be a vector space over the field F if there is a binary operation plus on V and if for every A belongs to F. So F means field, okay? And X belongs to, here X, Y also they will take in a textbook. You may consider a U comma V or X comma Y comma Z, or this is W, okay? So either X, Y, Z you can take or U, V, W. Here, but the scalars are A comma B comma C. And for the vectors, you have one operation that is plus. For the field, you will have the operation plus comma dot. Okay, that is with respect of addition and with respect of multiplication, we'll do the field of scalars. And for the vector, we'll use only, that is the operation, we call it as addition. So for the addition means, you'll have like this. That is U comma V belongs to V. So U plus V also, U comma V belongs to capital V. So you write like this. Or else X comma Y belongs to V. Then implies X plus Y also should belongs to V. Okay. V means here, when you do the addition of those two vectors, then you will get the element, whatever the element you are getting, that belongs to the vector V. Okay. And here A into, when we are doing for the scalar, A is the scalar here, dot U is the vector. Okay. So that only you have in the definition. That is A belongs to F and X belongs to V. There is a defined such that AX in V. That is A into U also belongs to V. A is here scalar, that is F, and U is here belongs to V. So then A into U, that is if A belongs to scalar and U belongs to vector, then whatever the resultant you are getting, that is AU, when you do the multiplication, that is scalar multiplication we call it, AU, whatever you are doing, that should be belongs to V. So this is from field of scalars and this is from field of vectors. So when you do the multiplication of these two, whatever the resultant you are getting, that belongs to vectors, not scalars. That means AU, it is not belonging to F, it is belonging to vectors. So if it satisfies this property and this property, and after that V comma plus is an abelian group. First one, first property is V comma plus is an abelian group. Abelian group means what? Again, 5 properties are there. No, first one is closure, second one is associative, third one is additive identity, and fourth one is additive, inverse, and fifth one is commutative property. That means in first point is there, no, V comma plus is an abelian group. Means abelian group means these 5 properties it has to satisfy. Okay. So next second property is A into X plus Y equals to AX plus AY. Okay. This is the second property. And third one is A plus B into X is equals to AX plus BX. A plus B. See second one, see A belongs to scalars. And here X comma Y belongs to vectors. Okay. So A into X plus Y is equals to AX plus AY. Okay. AX plus AY. So here again AX. This is scalar. This is vector. This is scalar. This is vector means again this is vector plus vector. Vector plus vector means again this belongs to V. So this is the second property. First you have to solve these all 5 properties. After fifth, this is the sixth one. Next seventh one is A plus B into X. That is AX plus BX. This is A is scalar, X is vector. Again this also belongs to vector only. So fifth, sixth, seventh property. After that seventh property, multiplication is there. Scalar multiplication, no? That is AB into X equals to A into BX. Okay. This is nothing but associative property with respect to multiplication. Okay. With respect to multiplication. AB into X, just you have taken A outside and BX. So this is the associative property with respect to multiplication. This is 5, this is 6, 7, and this is 8. And ninth one is, that is identity. Multiplicative identity is there, no? So before we have seen all the properties with respect to of addition, identity element is 0. With respect of multiplication, identity element is 1. If you remember about groups or rings, A into 1 is equals to 1 into A is equals to A. So whatever 1 is there, 1 is called as multiplicative identity. Here, before 1, 0 is called as additive identity. So ninth property is I into X. That is 1 into X equals to X. Okay. 1 into X equals to X for all X belongs to B, where 1 is the multiplicative identity in F. So if any numbers or any set if satisfy these all properties, then we call it as a vector space. This definition is important, whatever you have in your test book, that you try to practice that one and see the examples are there. The set of real numbers R form a vector space over itself, and R is a vector space over the set of rational numbers Q. And Q is a vector space over R. That is Q is a vector space over itself on Q only, and set of real numbers also vector space over itself. That is R. We'll write it as like this. R over R means it is real numbers or vector space over real numbers itself. And here we'll take whatever the field of scalars are there, no? We'll take the numbers as the real numbers or complex numbers. Only 2 type of numbers we'll take as a scalars. That is the real numbers or complex numbers. Okay, this is the important one here. So after that, subspace definition is there. This subspace is similar as subgroup or subring. So we'll denote it as capital W. If it is satisfies all the properties of V, then we call it as a subspace. But some definitions are there. Actually, for the definition of subspace, you have 4 theorems are there. In 4 theorems, the definition of subspace is defined. So from that, 2 definitions are given in the textbook, page number 5. That is let V be a vector space over a field F, a non-empty subset W of V is called a subspace of V if the following are satisfied. Okay. So if we'll take any set W, which is subset of V. Okay. W is any set, we are taking it as some elements are there in this, which is subset of V. So to become it as a subspace, it has to satisfy these all properties. Okay. So that is a lengthy process, no? So that's why some shortcut they have given for the any set to become a subspace. That is, if it satisfy the two are there, no? Two conditions are there. If it satisfy these two conditions, then we call it W as a subspace of V. Okay. That first condition is X comma Y belongs to W. Then X plus Y means addition of those two vectors. Here X and Y are two vectors from the set W. So if the addition of those two vectors also, you are getting the vector from the set W, then we call it as a first condition, it is satisfied. Okay. Second condition is if X belongs to W and A belongs to F, then whatever AX is there, if it also belongs to W, then whatever the set W is there, it is called as a subspace. Okay. Or else after that one more definition is there. This is also considered as a definition of the subspace. It can be easily verified that a non-empty subset W of V is a subspace if and only if X comma Y belongs to W and A comma B belongs to A comma B belongs to F. That is, F means scalars. So first condition to subspace. So this definition is also asked in the examination. Subspace means first definition. If X comma Y belongs to W, then X plus Y also should belongs to W. And second one is if A belongs to F and X belongs to W, implies X also should belongs to W. This is first one. And this is the first definition. And second one is X comma Y belongs to W, A comma B belongs to F. That means these are scalars and these are vectors. Okay. Then what we have implies AX plus BY, if it belongs to W, then W is called as a subspace of V. Okay. So these two definitions are important. Anyone you remember, and in the examination for 2 marks, if it is asking the question, 2 marks definition will be there and 3 marks you will have one small theorem on regarding of subspace. Okay. Next we have the concept of the linear combination is there. Linear combination means it is the combination of vectors and also scalars. Okay. So vectors means usually we denote it as V equals to U1, U2, U3, like that all vectors will be there. And scalar means, you know, that is we'll take it as A, B, C like that. So next we have linear combination. So these are all definitions, whatever I am telling, these are important for the examination point of view. First one is vector space. Second one is subspace. Third one is the linear combination. Next we have the even linear span is there. Okay. Linear span also, it is also important one. So these all come under first unit only. So second unit you have basis and dimensions is there. So second unit, basis and dimension. Third one is the coefficient space is there. Okay. So if you'll go to the important questions or important topics in the block 1. In first unit, vector space definition and example of vector space. Okay. And theorems are yes, what do you want, ma? Okay. Here next subspace is there, no? Subspace definition you see. After that, 6th page number theorem is there, no? Let V be a vector space over a field F, then the intersection of any class of subspaces of V is again a subspace of V. And in check your progress, you have proved that union, that is union of subspaces of a vector space, need not be subspace. And 7th page number, theorem is there. And 8th page number, 1.4.1, 1.4.3, these theorems. And 10th page number, 1.4.6. So these theorems are the important one. So in first unit, you have the concept of vector space, subspace, linear span. On this only you have all the theorems are there. Okay. Even if you see the model examination are there, no, means how the questions will be asked in the examination. First question is important one. Concept of a vector space and give 2 examples of vector space. Next, second question. Whatever. Next part. Okay, these are the concepts important in first unit. So page number 11, if you'll see how the examination questions will be there, that is the first one is define the concept of vector space and give 2 examples. And second one is define the concept of whatever the subspace is there, that one. On that, you have the 2 questions are there. So first one is proving that intersection of any class of subspaces is again a subspace. This you will get for 5 marks. And second one is this same? This is the intersection, no? Similarly, whether the union is also same. Union of any 2 vectors is again a subspace or not. That also you have for the 5 marks question. Means actually here combination of 2 questions is there. It is splitted as 2 questions. Okay, combination of 2 questions are there in 1 question for the long answer. Long answer. Okay, so that it will be splitted into 2 questions. One is for the intersection you will get. Another one you will get for the union. Okay, and next section B, 1.7.3. This, if you know the concept of linear span, this is the important question. This you will get for the 5 marks, or else sometimes it is asked for 10 marks question also. So definition is there, and also proving the theorem is there. Okay. Next, if we'll go to the basis and dimension, in this regarding of the basis and dimensions, you have some, again in this also you have all the theorems are there. So page number 14, one theorem is there. Page number 17, 2.3.3. So this is the important theorem. Next, in this only linearly independent and linearly dependent vectors are there. Linearly independent, linearly dependent vectors. So that if you know the definition, if you know the definition of linear combination, then we can find which vectors are linearly independent and which vectors are linearly dependent. Okay, linear combination means V of F, if it is any vector subspace such that we have taken a V of F is a be a vector space, then here U1 comma U2 comma U3 so on, it belongs to V. Okay, V means vectors. And if you are taking A1 comma A2 comma A3, this belongs to field of scalars. Then the combination of these two, combining of these two, that is A1 U1 plus A2 U2 plus A3 U3 so on. Okay, this combination of vectors and also scalars, if you write like this, then we call it as a linear combination. Okay, this is called as linear combination of vectors. So usually in linear equations we'll write now, that is 1 0 0 if any vector is there. So we'll write it as A into, that is A1. This is any scalar. plus A2 into 1, 0, 0. So when you add these two, what you'll get? A1 is into 0. So this you are getting plus A2 into 1. So you'll get 1. So we miss in linear equations also we'll write like this. It is in the form of, that is A1, A2, A3. These are scalars and these are vectors. So vector anyone, you can write it in the form of first vector and it is divided as vector V and V1 plus V2. Okay. So that is a definition of linear combination of vectors. Next, in this only linearly independent and linearly dependent vectors are there. So linearly dependent and independent vectors means whatever the linear combination when you are writing. So not all, whatever the scalars are there, that means A1, A2, A3. They are not, all values are not zeros. Okay, some values you will get non-zeros also. Then such type of vectors are called linearly independent vectors. Okay. So if you get A1, A2, A3, all are equals to 0, then we call them as linearly dependent vectors. Okay, the definition you have in the textbook. So you can see the definition of that one. Linearly dependent and linearly independent vectors. So linear combination you have seen, no? So from this only we can tell that so linearly dependent vectors. Definition is let V of F be a vector space, a set of vectors V1, V2 up till Vn belongs to F is said to be linearly dependent vectors. If there exist A1, A2, A3 up till An belongs to F, not all 0, such that A1, V1 plus A2, V2 up till An, Vn is equals to 0 vector. Okay. Here, if you see in the, just 1 minute. In vectors, we'll write the 0 vector as like this. Okay. In your textbook, here it is, whatever the O is there or 0, it has written as bold one. So this is called as 0 vector. Even this is also same, 0 vector. Okay. You can represent, if you have any confusion of this one, if only like this it is written, it is called as a scalar. For scalar 0 means that is real number. No? This is regarding of scalar. If you have the bold 0, then we call it as a 0 vector, or else 0 on that. If arrow mark is there, then also it is called as 0 vector. Okay. Linear combination means here these whatever the vectors are there, u1, u2, u3 and multiplication of this one. Okay. So linearly dependent vectors means here whatever you are writing linear combination A1, U1 plus A2, U2 so on up till AN, UN. So if it is equals to 0 vector, that is not all 0. Not all 0. That means this A1, A2, A3, A4 up till AN are there, no? These scalars. Not all 0 means some scalars may be 0, some scalars are there which are not 0. So such type of vectors are called as linearly dependent vectors. Okay. Next, linearly independent vectors. Linearly independent vectors. So in this A1, U1, A2, U2, so on up till AN, UN equals to 0. In this, all whatever the scalars are there, A1, A2, A3 up till AN. That is A1 equals to A2 equals to AN is A3 equals to so on up till AN. These all are 0. Okay. If all the scalar values are 0, then we call it as a linearly independent vectors. In this, whatever the scalars are there, some may be 0, but not all 0. Some may, you will get the other numbers rather than 0. Then we call that vectors as linearly dependent vectors. If all these values, whatever A1, A2, A3, all you are getting as 0, then we call linearly independent vectors. Okay, on this you will have problem also. On linearly independent vectors, problem you will get for the 5 marks question. And one problem you will get on linear combination also. Okay, so 2 vectors will be given. So from that you have to write the linear combination of that one. This is for 5 marks, and this linearly independent vectors also for 5 marks you will get the question. Okay, so these problems you will get from this second unit. In basis and dimensions, you have the linear combination of vectors. So in basis and dimensions, some important questions are there. That also theorems are there. So you can see them. Next, third unit. So 2 10 marks questions. One you will get from the unit 1. And next you may get for the quotient space is there. Quotient space, you have one theorem is there. Regarding of that is a finite generated vector space V over a field F, then W and V by W are both finitely generated. So quotient group is there, no? If you have idea in groups, quotient group G by N. Okay, like this it is denoted. Same, similarly you have the quotient space is there. Even quotient ring is also there. Whatever the definition you have, similarly you have the definition of quotient space. In this, only two theorems are there which you will get for the 10 marks question. That is in page number 26. Let W be a subspace of a finitely generated vector space V over a field F. Then W and V by W are both finitely generated, and this is the important one. Okay, this is dimension of F, V by F. So this is quotient space. This, okay, this is the 10 marks question you will get in the section B. And after that, one more question is there, which you will get for the 10 marks. That is a worked out exercise is there, no? 3.4.1 exercise you have. Same, similarly will be there. Just a slight difference you have in the question. So this is also same dimension of this whatever DIM is there, no? This is the short form of dimension of vector space. Dimension of vector space. You can write shortcut as V dot S. Okay. Vector space dimension is nothing but in a set how many bases are there. If you count that one, that is called as a dimension of the vector. So these two 3.3.3 theorem and 3.4.1 exercise, whatever theorem is there, these two are important questions, 10 marks questions in third unit. Okay. If you go to the second block, it is a linear.
Madam, in second unit?
Amma?
In second unit, what are the important questions?
Second unit, I have told one theorem, no? Page number 17. Suppose B is equals to x1, x2, up till xn is a basis for a vector space V over a field F, and y1 comma y2 comma ym is a linearly independent set in V, then m is less than or equals to n.
Ma'am, thank you.
The 10 marks question.
Okay.
You can see the length of the theorem. It is very big one. And the short answers, I think so. Short answers are not this one. 19th page number is there, no? 19th page number 2.4.3. This is a linearly independent, just now I have told, no? On this problem, this is. That is x1 is equals to 3 comma 1 comma 0 comma 0, x2 equals to 0 comma 2 comma minus 1 comma 0, and x3 equals to 0 comma 0 comma 4. This is called as R to the power of 4, means it is the vector space over R with 4, whatever the elements are there, no? R to the power of 4 means you will have the elements as 4 elements. If R to the power of 3 is there, means standard basis, in that you will have 3 elements. Standard basis will be there. So standard basis means if R2 means you will have like this elements 1 comma 0, 0 comma 1. Okay. So R3 means it is 1 comma 0 comma 0. Next 0 comma 1 comma 0 comma 0 comma 0 comma 1. Okay. R to the power of 4 means you will have same like this only. You will have the identity elements will be there, no? This is 1. Next 0 comma 1 comma 0 comma 0. So on. Okay. Last will be 0 comma 0 comma 0 comma 1. Okay. So these are called as a standard basis. So R2 means whatever the vector set is there, in that you will have here whatever the set is there, no, it contains 2 elements. So this is 1 element and this is another one. R3 means this is 1, 2, 3. Next R4 means this is 1, 2, 3, again one more, that is a 4 you will have. So that is here R to the power of 4 over R means R to the power of 4 is the elements, how many elements are there in the set with respect to of the real numbers R. Okay. So if you'll see, suppose A1, A2, A3 belongs to R such that A1 into X1. In place of U1, U2, we are writing X1, X2, X3. You are multiplying with those elements of R to the power of 4. Then you will get all A1, A2, A3 values are 0. If you'll see back set 20 page number. When you do the simplification of that one, you are getting all the values A1, A2, A3 values as 0. So if you are getting all these values as 0, then we call the given vectors are linearly independent vectors. And this is the important for 5 marks question. Okay. And next 2.4.6 theorem also. This is the 10 marks theorem. 2.4.6 theorem. Next we have quotient space. In that, check your progress. You have for any x comma y belongs to V, x plus w equals to y plus w if and only if x minus y belongs to w. That one, and second one also, any two cossets. So actually this is the question, no? But the framing of the question you have in the model examination question. That is, prove that any two cossets of W are either disjoint or equal. Flask. Okay. So if you'll see 29 page number long answers. So framing of the questions will be like this. Just now I have told, no? Theorem 26 theorem, 26 page number theorem and 27 page number theorem. That are the questions of 3.7.1, 3.7.2. Okay, these two are 10 marks questions in third unit, and 3.7.3 is the 5 marks question. Okay. So almost from the first unit, you will get the 5 marks questions and small theorems are there. From the second unit and from the third unit, you will get the 10 marks questions. So second one is the linear transformation is there. So linear transformation is similar to the homomorphism of groups. So if you remember the homomorphism of groups and also homomorphism of rings. So similarly, you will have here the linear transformation. So this also you will have the definition. What is linear transformation? This is also definition is asked in the examination. And regarding of that, what are the properties of that one? With the help of that, some theorems are there and even problems also asked for the linear transformation. So linear transformation, almost it is similar as homomorphism. So homomorphism is mapping is there, no? Mapping between the two sets will be there. One will be the vectors you will have and another one will be the field of scalars you will have, u comma v. So with the help of that linear transformation, some definition is there. So definition is asked in the examination and also problems are there for linear transformation. So you have to show whether the given one is satisfying the properties of linear transformation, whether it is a linear transformation or not. Okay. So it is similar as a mapping. Function was there, no one. Two sets will be there like this mapping we have done, no. So far it is similar as the homomorphism of rings or groups. Okay, groups and also rings. Similarly, you have for vector space, we call it as a linear transformation. Linear transformation. So linear transformation, here also mapping will be there like this. Okay. So this is u of f, capital U is. Here we have f and g, no? Mapping between f and g will be there. Here in vector space u and this is v, v of f. Okay. So in this the elements will be, that is u will be there. Here t of u. This is the image of this one. This element you have here. If you know, this is the domain and this is the codomain. And whatever the elements are there here, when you are mapping with them, then we call it as whatever these elements you are getting, these are the images of that one. Okay, T of U is the image of U. Okay, so U is the element in U of F and V of F you have the mapping. T in the sense transformation. Okay, that is the image of U. And U plus V, we'll get it as T of U plus V. Next we have V, T of V. Next A into U. Next A into T of U. Okay. This is the mapping of like this. Okay. This is with respect of vector addition and scalar multiplication. This is definition of linear transformation is T into V equals to T of U plus T of V. Okay. This is with respect of vector addition. Okay. Next second one is T of A comma A into U is equals to A into T of U. This is called as scalar multiplication. Okay. Combination of these two is the definition of linear transformation. So that you have in page number 32 page number. So that is let V and W. Here instead of U and V, he has taken V and W. That is here V and we can take here W. Okay. V and W be two vector spaces over a field F, a mapping from here U to V. F is a mapping from U to V. In the textbook, it is given that V to W. Okay. Mapping. Mapping means this one. Okay. So that it F is mapping from V to W is called a linear transformation if property is if it satisfies, that is F into A alpha plus B beta is equals to A into F of alpha plus B into F of beta. Combination of these two definitions, it is given like this. That is f of a into alpha plus b into beta equals, in the textbook it is given a into f of v is there. You correct that one, it is alpha. Okay. A into f of alpha plus b into f of beta, where alpha comma beta belongs to v and a comma b belongs to f, that means scalars. So if you remember this one, it is useful for solving the problems. That is f of a into alpha plus b into beta. Alpha and beta are the vectors here. Instead of u and v, he has taken alpha and beta. Okay. So a and whatever a is there, a is the scalars are there. Means these will be numbers and these are the vectors, real numbers. So f of a into alpha plus b into beta equals to the scalar you are taking outside, f of alpha plus b into f of beta. If this property satisfies, then we call it as a linear transformation of vector space. Okay. So definition is important. After the definition, problems are there. Problems means okay. Theorem is a 38 page number 4.3.4. This is the important one. That is, if v comma w are two finite dimensional vector space over f of dimension m comma n respectively, then dimension of homomorphism of v comma w is mn. Okay, this is the 10 marks. Next, page number 40, you have problems are there. These are all 4.4.3, 4.4.4. These are the 5 marks questions. Okay. So whether given function, that is a given mapping, is a linear transformation or not. How to solve? These are the example problems. These problems are very important. 4.4.4, 4.4.3. So you will get for 5 marks question, and also sometimes you may get for the 10 marks question. Okay. Next week we'll see unit 5, rank and nullity is there. This is the important unit. Definition of rank and nullity, and also one theorem is there. Rank and nullity theorem. This is important. You will get this question for the 10 marks question. This is a very, which one? 44 page number. Definitions are there. What is rank and what is nullity? And this theorem is called as rank and nullity theorem. Okay. Next, page number 48. 5.3.5 is there, no? This theorem is called as fundamental theorem of homomorphism of vector space. So if you remember in groups, fundamental theorem of homomorphism of groups is there. Fundamental theorem of homomorphism of rings is there. Similarly, this is fundamental theorem of homomorphism of vector space. That is 1-to-1 property, on-to property, homomorphism. If these all satisfy, then we call it as a fundamental theorem of homomorphism of groups. Here also similarly it will be there for the vector space also. In this, linear transformation is there. Homomorphism is there, no? If you remember in groups, kernel of a group is there, kernel of a ring is there. Similarly, here also kernel of linear transformation will be also there. Will represent with the capital K, no? That you have the concept for the rank and nullity. So rank and nullity is the important one. That is, definition will be asked what is a nullity and what is a rank and what is a combination of those two. You have that this theorem is there. Okay. So next week we'll see the other topics, and third block is a important one. So whatever the matrix concepts are there, rank of the matrix and finding the determinant and finding the converting the given 4x4 matrix or 4x3 matrix, converting it into normal form. And in this, even in intermediate, if you have idea, Cayley-Hamilton theorem is there. So verification of Cayley-Hamilton theorem is also important one, and finding the roots. So if you remember in Cayley-Hamilton theorem, we'll find a minus lambda into I equals to 0. This is called as characteristic equation. So with the help of this, we'll find characteristic roots. Okay. So third block is a somewhat easy one. In that you can score, that is 10 marks for the long answer and 10 for the two short answer questions. That is 20 marks easily you can score from the third block. Okay. So next week we'll see the other units.